Hey everybody, my name's Nathan Wilmot and this is my final year project, the design and build of a dynamic balance test rig for Mech 2360. My supervisor being Chris Wensrich. So the scope of this project was to design and build a dynamic balancing testing apparatus for Mech 2360. Now, the aim of this project was, as I said, to design and build this apparatus as an assessment piece to test students on their understanding of rotating bodies. For this assessment, the instructor needs to place weights onto the device. The device will be then spun up, tested, and students will then need to add weights in certain positions to rebalance the device. So that brings us to the constraints. So this device needs places where the instructor can add weights to induce the unbalanced nature. These unbalanced weights must be able to be hidden from student view. The students must then be able to place weights to dynamically balance the system. In terms of the size, the body must not be overly large, approximately 0.2 meters diameter and under half a meter in length. And most importantly, rotation must be safe for all participants. So just a little bit on the theory to understand some choices. So what is dynamic balance? Well, it's the condition when the axis of rotation is a principal axis of inertia on all points on the axis, including the center of mass. Secondly, when the net moments and inertial forces acting on the rotating shaft are equal to zero. That second dot point allows me to quantitatively discuss and calculate what is dynamic if the device is dynamically balanced. So to do that, we need the principle of angular momentum, which is the sum of external moments equals the rate of change of angular momentum, which is described by that first formula there. The sum of the moments about the origin equals the rate of change of angular momentum also about the origin. Now, that rate of change of angular momentum equals the moment of inertia times angular velocity squared. Now, that moment of inertia is actually a matrix, which is comprised of the products and moments of inertia. This describes distribution about the axes, and so once placed back into number 2, the expression labeled number 4 can be calculated and then transmitted to each directional component x, y, and z, as shown by expression number 5. Now, if the system is dynamically balanced, the products of inertia will then equal 0, and if it's at a constant angular velocity, those accelerations will reduce to 0, and all those moments will be cancelled out, making a dynamically balanced system. So my design. This is my final design. It has a central body for the supervisor to place weights on the inner hub surface and on the outside surface for the students to place their masses. It has 2 semicircular covers. I've just removed one from this image just to show the inner workings of the device. It's all machined from one part, so the shafts in the inside and on the outside are from the same billet, which is held in place by 2 pillow block bearings, which is then connected to the load cells and then onto the frame via mounts and spacers. To actually rotate the system, the motor bit on the left-hand side will be connected to a handheld RC plane starter motor, which will then spin it up to the required RPM. Now, to measure the actual angular velocity and the position of the forces that each load cell experience is through an absolute encoder on the right-hand side, kind of hidden in this image. So that allows the position of each peak and each local maximum and minimum of those force measurements by each load cell. So going through the electronics quickly, the change in forces are measured by the 2 load cells on each side. These are run through amplifiers to amplify that signal so it's actually usable. And then as just described with the absolute rotary encoder, that measures the position as well as the angular velocity as well. I'm using Arduino Uno purely because I've had experience with it and it is easier to program as well. Skip one there. So I have run analysis through MATLAB to theoretically determine the forces that each bearing or each load cell will take. This was done to ensure that the masses added on and the angular velocities were suitable and were a correct choice. And this graphs just show what would happen if unequal masses were placed on each side. So with this system, the students will gather data, will be given data outputted from the Arduino, and then they will be required to make graphs and use those graphs to determine where to put their masses and how much those masses will weigh. How to do that is by solving these system of equations. The two center of mass equations at the top will statically balance it, while the two reaction equations on the bottom will then allow dynamic balance as well. So once it's solved, this will be able to tell the students where and how much each mass should be. To ensure that the load cells were a sufficient choice, FEA was done so that resonance was ensured to not be induced. As it's a cyclic load, these load cells would be acting similar to a spring, and so through this analysis it was determined that the stiffness of the load cells was a practical choice. So where do I have to go from here? I've created detailed engineering drawings of each component within this design. They just need to be toleranced and then sent away for manufacturing. I've also submitted a part order for each of the electronics, and I'm just waiting on. So where do I have to go from here? I have created detailed engineering drawings of each of the components of this design. Obviously not the load cells or the pillow block bearings, as they're to be bought in. I've also created a parts order for each of the electronic components I need, as well as the load cell and pillow block bearing of the mechanical design there. I just need to create tolerances for those drawings, and once that's completed, they will be sent off for manufacturing. And then waiting for manufacturing to happen, the parts will come back. Hopefully all the electronic components will be available to set up. I'll then need to create the code to calibrate each of the electrical components to make sure that the forces are being read as what's experienced, and then to make sure that's being outputted as a simple text file for the students to have for their assessment. Once the manufacturing is finished and all the parts returned, simple assembly will take place of the device. The electrical components will be hooked up. Then device testing will be performed to ensure that this project will near its completion, and that it will be sufficient for MEC 2360 assessment. So thanks for watching, guys. I hope you enjoyed this video.